So now we are listening to Denisa Martonová, which is a postdoctoral researcher at the Department of Mechanics of the university. The stage is yours, please.
Thank you. Let's try if this is working. Okay, so hello. So I will bring you again a little bit back from maths and bring you closer to mechanics. So we have seen a nice overview or presentation of how we can use AI in mechanics. I will be even more specific, and I will show you how we can use AI in biomechanics and specifically for cardiac tissue. So this is also a collaborative work of many people from many institutes and universities. And yeah, I will start with a small motivation of AI in biomechanics. Then I will just give you an overview of cardiac model itself. I will show you how we can model how we can obtain passive material models. Then I will introduce orthotropic constitutive neural networks, physics-informed neural networks. Then I will discuss how we can use regression in order to get a little bit more generalizable models. I will compare with other models in the literature. And lastly, I will discuss fiber dispersion, which you will see what it means. Okay, so let's have a look to this overview. You can see different biological tissues you can find in your body, and they are ordered by the stiffness. So in general, the stiffest tissues are the easiest to model, whereas the softest tissue are quite hard to model, and it's very hard to find the proper material model. As you have seen before, we engineers are always looking for some material models, which we can then feed into our equations. So my colleagues have discovered or have found with AI different models for almost all of the tissues. So for example, for brain, then for arteries or skin, or even, as you also have seen before, for artificial meats like tofu or tofurkey or whatever. In my talk, I will focus on cardiac tissue, which is quite complex. So it's orthotropic tissue, and I will show you how we could discover the best model for this. Why we are doing this? It's quite important because cardiovascular diseases are the leading cause of the death worldwide. So it's very good to have computational models which can help us to predict progression diseases rate, to help by the therapy planning, to help by investigation how to design some drugs, or how to design some devices, for example, in this specific case, for like heart pumps or other devices helping disease hearts. The latest computational model use AI, and as you can see here, it started about 2020, whereas the first models goes back to 50s, and they are very simple model, and it developed a lot, such that now we have quite advanced full heart models. So you can see here a simulation of my model I have used in my PhD, and this is rather simple model. It has just two chambers, like it's called biventricular models, and even this model has a lot of ingredients. So as you can see here, first of all, we need some clinical inputs in order of data, like these are measurement data, and then with this we can build up our computational model. Heart is a very specific tissue, and we need a lot of ingredients again, so we need a model for passive mechanics, but we also need some interaction with electrical parts, so we need a model for active mechanics, electrical excitation, because in heart you have like electrical signals which trigger the contraction. Then we need a model for hemodynamics and, of course, a geometry. This is obtained usually from MRI data, and they include also fiber orientation. So now having this, we proceed with numerical solution. Usually we use finite element methods. It's the gold standard in mathematical modeling. Then we have to verify and, of course, validate the model. And here, very, very essential is, again, to speak to clinicians in order to have some meaningful interpretations and to put it again or back to the clinical context. So now a little bit of maths or of engineering, so how we can translate this model into equations. So HART, as I said, is electromechanically coupled, so we have at least two field variables. This is the placement in the computational domain. The domain here is the left ventricle or biventricular model, and then we have transmembrane potential, and we have to fulfill the standard equation. This is the balance of linear momentum. Here you can see that with S we denote the stress, and we can decouple the stress into the passive part, which is the focus of our work in the model discovery. But we also have active part, which causes like the contraction based on the electrical impulse. The second equation is the evolution of the transmembrane potential, which is exactly this, what describes this potential development dependent on the time. Then, of course, we have to have some boundary conditions, like the Dirichlet boundary condition. This means that we have to fix the heart somehow in the place, or we have to define interaction with surrounding tissue. And Neumann boundary condition means that first we have to define traction, and secondly, also we have to define blood flow. This is usually modeled with Wind-Kessel model, and this simply means that we prescribe pressure on the endocardium. This is the inner wall of the ventricle. Good, now having all these equations, we have also to focus on the structure, or we have to keep in mind how the structure of the heart is. This is a very specific tissue, and it's maybe one of the most complicated. We can have a look because it's orthotropic tissue. This means that we have three directions. These are the fiber directions. These are myofibers, so the muscles. Then we have sheath. This is the organization you see here, that the fibers are designed in some sheath layers. And then, of course, we need a third direction, which is orthogonal to these both two directions, and this is the sheath normal direction. Especially, heart is very interesting regarding the fiber direction, because the fibers are rotating from minus 60 degrees on the endocardium, this is the inner wall, to plus 60 degrees on the epicardium, which is the outer wall, and it's like a onion. You can interpret it as onion layers, as you can see here on the picture. Good, now keeping this in mind, there is a very famous study which measured the stress-strain ratios in human myocardium. To my best knowledge, is the only one study which really measured on human specimens which are taken out from the body. It was post-mortem, and they really related stresses and strains such that we can obtain these curves. They did bioaxial extension tests, so they put in two directions, and also shear tests in all possible 6 directions. So if you have cubic specimen, then you have the orthotropy, you can shear in 3 times 2 directions. So now we have this experimental data, and what can we do with the data in order to obtain some model? So the very classical way in engineering is, okay, we choose one of the models we find in the literature, and we feed it with the data and fit the best model parameters. But this is very subjective, and it depends on the modelers which model we choose, and we don't know if it's the best model we could choose. The other way would be just to use neural networks to do this job for us. But the problem is, as you also have seen in the first talk, that such networks can violate physics, so it's not the best way to choose just very general neural networks, because also the weights are non-interpretable, and we as engineers are quite unhappy with this. The third option would be to use physics-informed neural networks or constitutive neural networks, which already hardwire physics into the architecture, so that they are thermodynamically consistent and the weights have meaningful interpretations. So we have chosen like this third option to find the best model for human myocardium, and we proceed with this. And so we designed such a network which is orthotropic and which already hardwires physics into it. So this means that instead that deformation is our network input, we input invariance into the network. So as we have orthotropic tissue, we have defined 8 invariants being the network input, and then we propose 2 layers. The first layer applies powers to these invariants. The second one applies exponential and identity functions, which are all convex. And the network output is free energy function from which we can again derive stresses. So in general, we have like very general free energy function here, which hypothetically could be our output. So in total, we have like 2 to the power 32 possible models. Good, now we start the training, or we train this network you have seen with the data. We first started with training only on biaxial extension data. And like these plots just mean that in the first line you have the data from shear experiments, and in the second 2 lines you have biaxial experiments in different ratios. And the colors means that each color represents one specific term. So if the term is activated, you see how much the contribution is from this term you see in this legend. But most important on this slide, you see, okay, we train with the biaxial data, so the prediction for shear data completely fails. This is maybe not so surprising. And vice versa, when we train with triaxial shear experimental data, then the prediction for biaxial data is pretty poor. So in a third step, we train simultaneously on all the data we had, so from biaxial experiments and shear experimental data, and now we could obtain pretty good fitting results. However, if you look closer, for example, like here on this first line, third column, you see that some colors are just very little present. So this means that some terms are maybe not so important. So we have to introduce some regularization in our minimization problem. This is like the penalty parameter alpha, and we just investigated how big alpha should be in order to still have quite good fitting result, but less complex model. So you see here this in this table. So alpha equals 0 means we have no regularization at all. We have then more terms activated. And with alpha 0.01, we have still quite good R squared, but we have only 4 terms activated. If you are not familiar with R squared, we usually use it in biomechanics or in engineering to characterize the goodness of the fit. So R squared equal 1 means we have a perfect fit. R squared 0 means the fit is not good at all. So here you can, or we could define the best model for myocardium with specific regularization alpha 0.01. And this is like 4-term model, which depends specifically on the second invariant, and 2 fourth invariants, 1 in fiber direction and 1 in normal direction, and 1 coupling invariant between fiber and G direction. So here we also use this covered model in the simulation of passive diastolic feeling. This means that we put stress on our biventricular model to mimic cardiac feeling. This means when blood flows into your ventricle, then it causes stresses on the endocardial wall. In the next step, we compared with other models which are usually available in the literature. These are especially two models, Holz-Apfel-Ogden model and Guan model, which are pretty similar, but as when you look closer, then we have different invariants which are activated, especially like both models use the first invariant for the isotropic part instead of the second invariant, which has been discovered. And this causes that the discovered model has much better or way better goodness of the fit measured by R². Good, so I still have a couple of minutes left, and here I would like to introduce our next step in the approach. I have showed you that myocardium is orthotropic. This means we have three different directions, fiber sheets and normals. But this is very idealized case, and in biomechanics or in living tissues, nothing is straight aligned. So usually these fiber sheets and normals somehow vary, and there is some distributions in this. So this is like denoted by the blue cones, and we can like assume that the fibers and the other fiber families are located within these cones with some probability density function, and this we can model with different approaches. There is one which is very easy to apply, and therefore we have followed this approach. It's called general structural tensor approach, such that if we assume axisymmetric distribution, then we can characterize everything just with a single scalar value kappa. So you see here that HI is the structure tensor, and this is depending on the identity multiplied by some scalar kappa value, plus then the tensor for the fiber family, again scaled by the kappa value. So here you can see two extreme cases when kappa is equal 0. Then we have perfect fiber alignment. This was the assumption so far. So this means dispersion angle is 0, and all the fibers lie on this line. The second extreme case is isotropic fiber distributions. This means that the fibers can lie anywhere on the sphere. So kappa value is equal 1/3. And you see that we have uniform distribution, or that the fibers can lay on the sphere, or anything between. Good, so to recall, our network with perfect fiber alignment has as input 8 invariants, and especially invariants I would like to focus on are in fiber, sheet, and normal direction, the 4 invariants. Here you can explicitly compute them by assuming some specific fiber, sheet, and normal direction. And this changes if we assume some distribution, then we can formulate the invariants, so-called distributed invariants in fiber, sheet, and normal directions, such that we double contract the Cauchy stress tensor with the structural tensors, and here we just plug in the equations such that we weight with some kappa values. Especially here, if we set kappa equals 0, then we recall the previous invariants. Good, and the loss function is the same, and the procedure is the same as before. So we have to minimize over the loss function containing the stresses, the measured stresses, and the model stresses, again with some regularization term. And we did this for different kappa values. So as you can see here in the table, we vary kappa from 0 to 1/3. And we could observe that including some small dispersion, which is first of all very physiological, but also we experienced that it fits much better with experimental data because R² was elevated from 0.89 to 0.9. So we can conclude that including some dispersion in modeling can also help to improve fitting results and is physiological in this stage. So again, these plots you have seen before, we could again rediscover four-term model also with dispersion with slightly improved goodness of fits. And here again, the colors represent the contribution of the specific terms visible in the legend here. Good, this is the same plot for this isotropic distribution where we set kappas to 1/3. What is interesting here, kappa 1/3 means that we have isotropic distribution. This means that, as I said, the second line is for stretch in the fiber direction, and the third line is for the stretch in the normal directions. If we assume uniform distributions, then rescaling the y-axis leads to exactly the same plots. So this means that now we cannot like differentiate between fibers, normal, and sheets, especially like here in the biaxial experiments. Good, so here I would like to sum up. So I try to show you how we used AI or physics-informed neural networks to discover a very specific model for human myocardium. Here we could discover a four-term model depending on one isotropic invariant, which is the second invariant, and two invariants in fiber and normal direction, and one coupling invariant. We have also shown that rich training data is critical to discover more generalizable models. We have also seen that including sparse regression helps us to get more interpretable models. And lastly, also including small dispersion into this approach helps us to find better models or models which are more physiological. And like in also the general message is that including dispersion in modeling of biological tissues can in general improve the modeling. And with this, thanks for attention, and I am happy to answer your questions.
Okay, thank you. Are there other some questions? Yes.
It's actually a very quick curiosity. Thank you for the talk. Don't remember if you said this. How many data do you use to train this?
We don't have so many data. Like we had these 6 shear experiments. From this, I think we just used like 12 points. Okay. So it's very, very small data. These are the dots. Yeah, actually, if you count all the white dots together, then you have the data set. So it's quite small, but the point is that the model is quite complex. So you had to, yeah. So it takes some time.
Okay. Are there other questions? I also have a curiosity on data. Mm-hmm. You are using always noisy experimental data, right? But what if this data were biased? How do you consider this case?
I think like what I have shown here, these are not like really the measured data. They are already cleaned, and they are average across the samples.
Okay.
So we just use these data we have, and
okay. And then you derive the invariance with different laws,
yes.
Right?
Yes.
Okay.
The point is that like all these curves you have seen are in different directions. So it's like multi-axial loading protocols or loading modes, and yeah, we just use these what we have, and it's quite like hard to have data for human specimens. So I think this is the only one study we have, and we tried just to use these data.
Yeah, I see. Okay, thank you. Okay, if there are no other questions, we can thank our speaker again.